Hi, you know me. I'm Nolan. We do this every week. That week being week 4, spring 2025. We're going to go through the poll fairly quickly. It's a nice short one. It does have some very important and commonly confused concepts. So let's jump right in. The first question is asking you to compare some similar but definitely different functions. We've got table, we've got order, we've got unique, we've got sort. Let me kind of give these to you from an order of least to most complicated. Least complicated is unique. It just finds the unique values. So returns the data provided with duplicate values removed. Boom, unique. Very, very simple. Cool. Next up, I would say is probably sort, because sort, everyone wants to give sort extra abilities. And I to be fair, I want to give it extra abilities too. It does not have them. All it does is whatever you give it, and by it, I mean a vector, it sorts it, which is great. Super useful. It puts it in some sort of order. It does turn out that some computers put values in a different order than others, especially when symbols are involved. And so like here, it is going to be a vector that is then sorted or ordered, some version of that. So it returns a ordered version of the data that has been sorted. I was mean. Because I want you to contrast that with order itself. Order is a function that it's not that it does the ordering or does the sorting for you, but it produces an output that can then be used to order or used to sort something else. Oftentimes, what I'm using that for is analyzing like a column of a data frame or multiple columns of a data frame all inside of the order function. And then I'm using that output to then extract from the data frame, and that's what puts the data frame in the order I'm trying to put it in. So it's used indirectly in that way. And if you're not sure what I mean, look at like the intermediate step. So look at what order does, and then go look at one of my order examples and see how it is used contextually. It's used to do the extraction. Okay, so the answer there would be a vector of positions that could be used to sort the vector. And I was mean here, and I used like the word order and sort in the sort, and just the word sort and order. Ha! But you just need to kind of pay attention. The concept here is not that one sorts and the other one doesn't. It's that one directly sorts, one can be used for indirect sorting. All right, finally, table, the odd man out here, although it's somewhat related to unique, is it first finds each of the unique values, and then it counts how many occurred. Now, when passed a vector, it produces a vector output, just each of the different values. When passed something more complicated than a vector, it produces a more complicated output called a contingency table. And it can be a bit challenging to use. And so oftentimes whenever I'm using table, I'll do some sort of coercion downstream in order to like just get the data I want and get it outside of this class called table, which is just a bit of a confusing class. It also prints off characters without quotation marks. It's because it's actually part of the name of the object, which doesn't get quotation marks when printed, which can be confusing in itself. So just be aware of the issue that it has somewhat of a confusing way of being printed, and you may want to coerce it into different ways when using it. Just a tip. Next up, we are comparing grep, grepl, gsub, and equals equals. Now here the odd one out is equals equals. Equals equals is what is that? It's equals. Equality. Left equal to the right side. So it's got to be exact. No regex, no partial string matching. Exactly the left, exactly to the right. And so if I come through here, I can see, well, that's only true for equals equals. The rest have more flexibility. They can be made to do like the whole string, but equals equals only has that an option. Is that the only one? Probably. We'll go through the rest of these. Return the vector of index positions where the matches are true. That is grep. That's the definition of grep. None of the rest of these return a vector of positions, unless I guess you're starting. No, they all return logic, a character vector, and logic. Returns a logical vector of true or false depending on if a match was found. Oh, that's fun. Okay, grepl and equals equals. They both return logic. grepl with flexible match equals with exact match, but I guess both matches. Okay, returns a modified version of the X argument. You kind of have to know which one of these have X arguments. I don't actually know what the names of equals are because they just kind of have the argument left, argument right. They may use X, I don't know. But gsub, like the whole point of gsub is to find a match and then replace it. So even if like in reality that's just a new set of data spawned off of the original one, it's close enough to this definition. I don't love this one. I should probably rewrite that at some point, but that's the idea. I was trying to get you to think of gsub. It replaces parts of the text and returns the rest of it to you. Finds matches based on just parts of the compared values. In other words, it does partial string matching. That's going to be all of our regex using functions. Finds matches only on the entirety of the compared values. So that's our equals. And then finally, the regex is used, regular expressions, is used because it allows for partial string matching. So this and this, we're always going to be, you didn't see mine. Oh, you did. Okay, good. We're always going to be the same selections. I hope that helped. Go back and review. Like, you can do that. It does trip people up. So spend a little bit of time now, memorize it, and you'll move forward. All right, first example, super common. I usually am working with snip markers. My kind of transition into these like large variants are kind of a new thing for me. And so historically, my genetic markers were all able to be defined by a chromosome sequence or contig back when I was using really crappy genomes. Usually some sort of delimiter. So a delimiter is applying limits, so delimiter. And here it's a underscore, and that's what I used historically, followed by a position. So here 1, 2, 3, 4, here 5, 4, 3, 2. So position 1,234 base pairs, which is probably still in the telomere for a lot of the genomes that I would work with, but hey, it's an example. All right, so I am making a character vector called markervec from those two values. gsub is then going to go through those. It's going to look for matches to this regular expression pattern and is going to replace them with nothing, effectively deleting any text that it matches. Kind of a fun little trick there with gsub. So here I am going to look for literally the character underscore. Underscore is not a special character in regular expressions. Period is, asterisk is. So they have contextual meaning. Period, I guess period isn't contextual. Period is any character. Represents one example of any character. Now there are actually some exceptions like line break, but let's ignore that for now. So basically any character. And then the asterisk is weird. It modifies the preceding character. It allows that preceding character to repeat. Now, some students will think like, all right, this establishes what character it is, and then that allows it to repeat that character. That does turn out to not be how this works. How this ends up working is that it becomes the concept of any character 0 or more times. And that's what the asterisk does, 0 or more times. So that means that if to the left of my cursor was the end of the string, that would still be a match because that would be an underscore followed by 0 further characters. If to the left of my cursor was what the string was, that would still be a match. That would be an underscore followed by a 1. A 1 is a character, and there is one of them, so that falls within the range of 0 to infinite. And I could keep going down, but we can look at this whole string and underscore followed by 1, 2, 3, 4 total additional characters. That's totally fine. That's all one match, and it's replaced with nothing, leaving you with CHR3. And that's it. Vec2, oh, well, I can do this over. So over here, underscore followed by a bunch of characters. So it would be replaced with nothing, leaving me with CHR16. So in other words, the chromosome values. So Vec1 is going to end up holding my chromosome values. So these are both going to be character vectors. It's going to turn out Vec1 or Vec2 is not. Neither one of these will be able to be coerced into a numeric vector. Represents chromosome and position values. That's like the totality of marker vec, represents just the chromosome values. And it turns out we're going to see that this one is the positions. Let's go through that and see why. And so this is how actually a lot of my scripts would begin. I would pull out the chromosome information first, then I would pull out the position information using these regular expressions. Here, the only character that is well defined is underscore. You have to have an underscore in here for there to be a match. And except the difference being that here there is a flexible collection of symbols on the left side, which means that if the match is here, well, that's any character 0 or more times, in this case 1, 2, 3, 4 times. And so that can be effectively replaced with nothing. And so that would leave you with just quotation mark 1, 2, 3, 4. So by itself, it's still going to be a numeric vector. And it's because I have not put an as.numeric around it. Going to be the most commonly missed part of that question. This next one, same situation, any character, any number of time, any character, any number of time, but then ending in a underscore. It does go as far as it can, except there's only one underscore, so this is as far as it can go, and there still be a match. And so then it replaces that with nothing. All right, so able to be coerced into a numeric value using it as .numeric without creating ina values, and that only is true about vec2. The rest of these would become fully missing data if I ran as .numeric on them. And yeah, that's why it would represent the number. So typically what I would do is I would add as.numeric around vec2, and that would become my, my numeric values describing position. I really like this question. I don't know if I managed to word it well. I've tried a few times, to be honest. But what I am doing is I am demonstrating how I try to use grep to explore. I maybe will use gsub to fix like really specific things in a flexible way, but gsubs are dangerous because they're so flexible. If you're not being really smart and clever and thinking through all of the possible situations that might be occurring, or at least experimenting and seeing what all the possible situations that might be occurring are, gsub can just make changes that you're not aware of. So similar with grep, like if I take data that contains blue, navy blue, light blue, green and blue, blue with the space, and I search for just Lu, I will pull out all of those values because they're all matches that contain LUE. And that's what I'm searching for. So that's great. It's huge for exploration, super, super useful in large data sets. I use it all the time. But I don't typically assign to this, because if I assign to this, then I would replace it with whatever I assigned it. And some of these don't really all belong to blue. Like navy blue is really different from the rest of the blues. Green and blue, literally equal parts, two different colors. Yeah, I mean, it depends on, I guess, how you define green, but yeah. So I mean, it's a thing. So what I do when I am cleaning is I tend to use a much more safe approach, unless I've really researched what I'm doing. But like if it's a data set that may change quite quickly, like if it's survey data and I want to be able to add to it later, well, what I'll do is I may do some cleaning, like trim white space, like remove side like spaces on the side and fix capitalization. But then I'm going to probably be testing for exact values because it's very safe that this will only replace capital B LUE, nothing else. Blue with a space, not going to be a match. Navy blue, not going to be a match. Only fixes this. Only fixes this. These are very, very safe replacements. I also want to point out, though, R does show you, at least by default in RStudio, it'll show you what colors it knows, which is kind of cool. So you can see that color in my screenshot here. So that's the idea. The safety situation is, in summary, I guess what did I exactly ask? Why do I prefer to use whole string matching? Because it is safer to define exactly what I want replaced rather than use a flexible tool that may have unanticipated results. Something like that. All right. Now, finally, we have probably my most missed question, at least in some semesters. Percent and percent as well. But in this situation, it is asking really about this concept of greedy versus lazy. And if you're not picking that up, it's because you probably just forgot about it. And so the issue here is that if I start a match with CHR, so all of these start with CHR, so I match with CHR, and then I have some sort of flexibility. Well, if I want the flexibility to end here, then I need it to be able to span a variable width between the R and the underscore. So this example defines exactly one character and then a second character. They can be anything, but it's 2 total characters had to be between them. That would not work because 2 of these don't have 2 characters between them. Here, this one is not going to remove the underscore sometimes, and sometimes it's going to even leave. Like for this one, it would actually end up matching that 1 in that second dot. And so it'd end up removing that dot. So that'd be a problem. So that would be also bad. This one is pretty close, except the problem is it matches CHR. Then it's any character, any number of times, and then a underscore. So here is any character, here's an underscore. So that is technically a match, but there is a longer match that is possible. And because asterisk by itself extends as far as possible, it will end up matching this one. And so, yeah, so you match CHR at first, then it started to extend, it reached here, and then stopped because that was the longest, or that was the furthest it could expand and result in a match. So that's not the right answer. This one ends up being the right answer. The reason why is because the question mark following an asterisk makes that asterisk lazy. It means that the asterisk will stop expanding once it can. So here is CHR. Here it is followed by 0 characters, and then it could stop because that's an underscore. That's a match. And it will then keep searching, but there's no more CHR. So it doesn't keep replacing, and you end up with 1242 underscore 22233. Same thing here, CHR, then it starts looking for this flexible match. Here's one character, here's a second character, that's fine, and here's an underscore. Hey, that's a match, it stops because it's lazy. CHR, there's one character, and then the underscore after that, it replaces it with nothing, leaving you with the desired text, and boom, that's why it's the right answer. If that doesn't make sense, run back through that again, but that's the idea. So lazy versus greedy. Lazy stops when a match can be made. Greedy keeps going with the expansion as long as a match is possible. Now, it is different between longest and shortest. But yeah, otherwise, I hope that helped. Thank you. Have a good day.